Hi, in this video we are going to continue explaining the origin of the universe, and this time we will be focusing on elementary particles. Now in the last video we asserted that again there's this cycle of stars, right? And stars form from nebulae, and then stars mature, and then they die, and then when they die they scatter their remains all throughout space, which is the basis for the formation of another nebula that would create another star. So therefore, if we ask ourselves, okay, the solar system, well, it was created from a nebula, but that nebula was probably coming from older stars, and those older stars were coming from other older stars. And again, we believe that the sun is the second or third generation star. But if you think about it, it has to start somewhere. And when it started, we can imagine that it would start from the start of the chain of element formation, which is hydrogen. So therefore, we can imagine that before the second generation of stars, there was the first generation of stars, and that first generation of stars had helium. Okay, had helium, created the first stars. The stars died, created the first nebula, or second if you count this as the first one, and so the cycle continues. But ultimately, it started with hydrogen, or the lighter elements. So it's kind of really logical to say that hey, wait, hydrogen, helium, lithium, all of those are just atoms. And take for example hydrogen 1. Hydrogen 1 is simply hydrogen with one proton, no neutron. That's why its mass is 1. If you have hydrogen 2, that would be one proton, one neutron. That's why its mass is 2. If you have hydrogen 3, that would be one proton, two neutrons. That's why its mass is 3. By the way, this is sometimes called as hydrogen, and then deuterium, and then tritium. But that's hydrogen 1, hydrogen 2, hydrogen 3. So it's kind of like saying, okay, where did the hydrogen come from? Then realizing that hydrogen is really just protons and neutrons in combination. One proton if it's hydrogen 1, one proton and one neutron if it's hydrogen 2, one proton and two neutrons if it's hydrogen 3. But it's really a combination of protons and neutrons. So therefore, it's kind of like saying, okay, if I have a building, what's the origin of that building? Well, how was the building made? Well, buildings have different parts. It has the cement component, it has the metal component, and then you can ask yourself, okay, where did the metal come from? Where did the cement come from? So therefore, it's kind of like saying, okay, to explain the origin of where all the hydrogen came from, you kind of have to explain where the proton and the neutron came from, because after all, hydrogen is just an assembly of protons and neutrons. So if you can explain how neutrons and protons came about, then you could explain how we were able to create hydrogen. Right? So that's the logic. So scientists have been really at this, and they have realized, for example, in the past centuries, that things can be classified as mixtures, and these mixtures are just, coming from pure substances, the compounds, the elements, and elements are made up of atoms. And then they went further, and then they realized that an atom is just really made up of a proton, a neutron, and then maybe an electron revolving, orbiting around it. So now we know that atoms, which hydrogen, lithium, and helium are just really made up of three components: electrons, protons, and neutrons. Right? And then scientists went even further, and when we developed sophisticated material equipment, we actually found out that protons and neutrons are made up of what we call quarks. Okay? And then we realized that electron is just one of the many leptons. Okay? So I know this is just an extension. Just like saying, okay, if I have a proton and neutron, bind them together and I throw in an electron revolving around it, I now have an atom. We're just saying that protons are also made up of of even more elementary particles that we call quarks and even neutrons. And electron is an elementary particle, but it's just one of the flavors of leptons. Okay? So ultimately what we're saying is that we have elementary particles, and these elementary particles are called quarks and leptons. Okay, at least for the material part. There are other parts also that facilitate, for example, the presence of mass, the fundamental forces of the universe, the four fundamental forces. Remember, I kind of discussed that to you. Strong nuclear force, weak nuclear force, electromagnetic force, and gravity. Right? So, what do we know about this? By the way, if you're wondering, like, how did they know that, sir? And it's kind of like difficult to do. Well, remember when we discussed about static electricity? And one of the videos that I showed you was this person, and he was rubbing some kind of fleece material into a plastic material, and then because of that, he was able to attract the can of soft drinks. That's because when you rub things together, you build up static electricity, just like how the materials inside the protoplanetary disk rubbed with each other, built up static electricity, and that's why they clump together. But how is static electricity built up? Well, it's actually because you are transferring electrons. So when you rub something, when you rub your plastic comb into your dry hair, some electrons transfer, right? And therefore, that's why we knew there are electrons and that they are a separate component, because otherwise, if they're not separate component, why would they be transferred? So, and then we discovered that we can bombard electrons into gold foils, and then we realized that there is something there that kind of deflects the electron. So therefore, we experimented, and then later on we realized that we can have one atom and one atom, and then we can smash them together, and then it would basically disintegrate into these parts. Kind of like if you're wondering what are the components of a TV. Well, you get one TV and another TV, smash them together. When you smash them together, obviously they get destroyed. The internal parts would be exposed outside, and now you know what are the internal parts. Kind of similar. Again, I'm dumbing down these concepts to you so that it's easier, but the thing is, they can get one atom, another atom, and then smash them together. When they smash, obviously the parts, the constituents that make up the atoms would scatter, just like a TV. If you let it fall from a two-story building, its guts will spill out. But the thing is, you can see what are the components inside. Yes, some of the components might be broken, but at least you can see what is inside. Similar, but again, not the same. But you have two atoms, smash them together, you can see what is inside. And then from there, scientists deduced that ultimately the elementary particles are leptons and quarks. So what are these leptons and quarks? This is the map of it. So quarks have 6 flavors. So you have the up quark, the down quark, the first generation. The second generation are charm and strange, and the top and bottom are the third generation of quarks, right? And then for the leptons, the first generation is electrons and it's electron neutrino. And then the second is the muon and it's muon neutrino. The third one is the tau and the tau neutrino. And then after that, we can also have particles that is not for matter, but for the forces, for the energy. So the gluon is the particle for the strong nuclear force. In other words, the one that's responsible for the bond inside particles, inside nucleons of inside the nucleons of a nucleus of an atom. Photon is the carrier for the electromagnetic force, and then the Z and the Z and the W W bosons are the vector bosons for the weak force. And then we don't have gravity yet. And then we have the Higgs boson, which is the latest to be discovered. This is responsible for mass. Okay, why some particles have mass, some particles do not have mass. Again, kind of a higher concept, but what I really want you to understand is just this narrative that mixtures are made up of pure substances that are mixed together. Pure substances can either be electrons or compounds, but compounds are just made up of, elements and compounds, but compounds are just made up of elements, and these elements are just are just different atoms. But different atoms have constituent components called electrons, but even these components have smaller components, and these components are the elementary particles, namely the quarks and the leptons. And electron, technically speaking, is already an elementary particle, but it's just one of the generations of leptons. And again, as I showed you here, the electron is the first generation of leptons. The electron with its electron neutrino. Then there you have 3 generations of these. But again, the narrative is that even the atoms have components, and the components also have components, and you can have this hierarchy of organization up to the elementary particles, quarks and leptons. And again, remember, you have 3 generations of quarks and leptons, up quark and down quark for the first generation, charm and strange for the second, and then for the third generation, top and bottom. And the duration simply means the level of energy. So this has less energy, this has more, requires more energy, and this requires more energy also. Okay, so that's the idea. Now, after that, now that we know, for example, about quarks and leptons, we, for example, realize that a proton is simply made up of 2 up quarks and 1 down quark. Okay, and a neutron is something that is created when you have 2 down quarks and 1 up quark. And if you notice here, we only really use the first generation, right? So the matter that we see around the universe is just made up of the first generation of elementary particles. We just have up and down, 2 ups and 1 down to make proton, and 2 downs and 1 up to make neutrons, and then electron. And that's basically what constitutes all the matter that we see, all the hydrogen, all the helium, all the lithium, all of those other stuff. Okay, but again, they are quarks and leptons. Now, it started as like that, but remember how they realized that there are quarks? They have atoms, and these atoms, they smash them together. Okay, so they have this equipment called particle accelerators, like the Large Hadron Collider and the CERN. So you have these 2 particles, they let them move at very, very fast pace, and then they collide, and then when they collide, they kind of spill out their guts. And then when they spill out their guts, so to speak, we can kind of know what are the constituents. So sometime here, they realize that they can get some leptons. They can get strange top, bottom quark in some of the collisions. And again, the reason why they are called second generation, third generations, because they realize that charm and strange would only really appear if you have more energy put into them, and if you have top and bottom, even more energy. So the higher energy you use in the collisions, the more likely they will appear. So that means that these things are smaller. So this is bigger, this is smaller, and this is even smaller. So it's about the size. And why would it? Why would it require more energy if they are smaller? Again, I'm kind of dumbing this down for high school level, but it's kind of like how we use microscope. We use, oh well, I'll just use something that's familiar to you. You remember Blu-ray and the old DVDs, CDs? If you happen to be someone who's curious, if you look at the CD, the laser and DVD, the laser that is used here is colored red, while the laser that is used in Blu-ray is colored blue. That's why it's called Blu-ray, right? And you notice what's the difference in terms of amount of data they can store? This can store more data, and this can store less data. That's because in the Blu-ray, the holes that is read by the blue light are smaller compared to the DVD. The holes in the CD, because in the CD you have pits, and that is what is being read by the laser, are bigger. Okay, so therefore, if you have smaller holes, then you can fit in more data. But more importantly, in grade 7, you've learned that light is Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. And in terms of our eyes, we can really only recognize red, green, and blue. So let's just condense Roy G. Biv as red, green, and blue. Let's just pretend that this is the upper end, this is the middle end, and this part is the blue end. So, and if you remember, I hope you do remember this, blue light actually has the highest energy, and red has the lowest energy. Okay? So, to create blue light, you actually need more energy than to create red light. And what do you know? When you have red light, you can only read big holes. And when you have blue light, you can read small holes. That's by design. So in the same analogy, when you use big energy in the collisions, you're using blue light, which has more energy, you can read small particles. But if you are using less energy in the collisions, like red has less energy, you can only really detect big things. So that is the thing here. When you have collisions that are not so energetic, you can only get up and down quarks. But if you have bigger amounts of energy, you can have traces of charm and strange, and even bigger energies, you can have traces of top and bottom. So therefore, it tells you that these are bigger, these are smaller, and these are the smallest in the generations. Okay, and this is the electron. And just to kind of reiterate that concept, I need you to look at this video. This video, no, I don't want to infringe on any copyright, but this was created by. I'm sorry for the ad. This was created by a person, and it's actually copyrighted, I think. Yeah, by Carrie Huang. So credits to him. So this is the human being that's the size of an earthworm, dodo bird. So you can zoom in on it and find that you have smaller and smaller things like an ant, right? And the ant, you can find the human egg, and then infrared, right? So see, infrared. Remember, red light. Then violet light. See, violet light is smaller, so because it requires more energy. And then you have the phospholipid, DNA. And DNA, you have the X-ray, smaller. You have water molecule. And you have the hydrogen atom, helium atom. And then you have the picometer, that's even smaller. And then femtometer, you have the atoms, nucleus, neutrons. So you're getting smaller and smaller in scale here. And then these here, not sure, but this is our hunch. You have the up quark, the down quark. Strange quark are smaller. See, charm quark are smaller. Then bottom quark are even smaller. I mean, the top quark is even smaller. And then you go further inwards, and you have the Planck length. So this is the smallest scale that you can get. Okay. But more importantly, let me just pause here. You have a string. Right, so you know where I'm getting at here. I'm saying that from atoms, people think that it's made up of electrons, protons, and neutrons, and these in turns are really leptons and quarks. But there's even smaller structure in that, and that is called strings. Ring a bell? String theory. That's why people are hyped up about string theory, because they think strings are the ultimate. It is at the smallest scale, at the Planck length, the limit of the smallest length that you can have, and you have a string. And we just say that just like how combinations of quarks create the higher structures like protons and neutrons, we believe that strings also do that. Okay, we believe that, for example, a string can create a strange quark, it can create a top quark, it can create a Higgs, it can create boson, it can create all of these things. And that's why we chose the terminology string. Because again, if you have a string, like a guitar string, right? It depends on how big the string is, how thin the string is. Even if you have the same string, if you fret it here, it will sound different. If you fret it here, it would sound different. Meaning if I have a guitar, if I put my finger here and then pluck it, it has a different sound. If I put it here, fret it here, it creates a different sound. So therefore, just with one string, if it vibrates differently, you create different sound. So in the same manner, scientists are saying maybe we have strings fundamentally, and then depending on how they vibrate, they might create the elementary particles. And from there, the elementary particles would create the atomic, subatomic particles, and then subatomic particles create atoms, and the atoms create elements and compounds and mixtures and all the matter in the world. Okay? So again, that's important because after all, we are looking at the origin of the universe. But again, a warning. Yes, I name dropped string theory, but string theory is much deeper than this. Obviously, I'm dumbing down all of this for you, not because I think that you don't have the intellectual capacity for it, but I just think that, again, just like a building, you cannot build the 34th floor without building the 33rd floor, the second floor, the 12th floor. You have to build a lot of concepts before that in order to understand string theory better. But just because you can't understand string theory better, I don't want to not mention it. Because again, my goal here is to stir your imagination. My goal here is to capture your interest so that you can say that physics is so interesting that when you go to college, get a physics degree. If there would be students that would have physics degrees, it would be from our school, because our school boasts the best of the best. So therefore, that's my goal here. My goal is not really to pretend that I'm an expert at this. I myself do not understand a lot of these things, but I know enough to kind of present this to you in a way that it would interest you. That's the point. The point is not to pretend that I know this stuff and that I can teach you to learn this stuff in just a video. That's never the goal. So the idea is, again, when we trace the cycle of stars, it has to start with the primordial hydrogen because it starts there. But when we realize hydrogen is just made up of protons and neutrons, and these protons, neutrons, and electrons are just leptons, and these leptons are just made up of the elementary particles, and this gets us closer to understanding the universe. Because after all, if we have to explain where the universe came from, it must have come from the most basic elements of it, which to some string theorists, they believe that it's string theory. It's the answer. It's the theory of everything. From strings, you can create these elementary particles, and you can build up all the structure of the universe, even the forces and so on. Although there are still some problematic things like dark matter, dark energy. But the thing is, it's a start. Okay? So, those are the elementary particles. Again, you have the leptons and the quarks. And the quarks are 3 generations, up and down. Quark for the first generation, top and strange, and charm and strange, and top and bottom for the third generation. Then the first generation of leptons are electrons and electron neutrino. Second is muon and muon neutrino, tau and tau neutrino for the third one. And again, leptons, quarks, and then the last ones are the force particles. So these are the generation of matter. So these are what makes matter, and these are what makes forces or energy. So remember, there are only 2 fundamental things in the universe: matter or energy. Anything that has mass and it can occupy space, it's matter. Anything that do not fall under that category is probably energy. So for example, again, a silly analogy of mine, but it works all the time. This, it has mass and it occupies a certain volume, space, so it's matter. Sound, however, does not do that. So if I have a weighing scale and I shout to the weighing scale, ah! Or maybe I have a weighing scale and then I shine a flashlight onto it, the weighing scale will not feel mass from the light, because light is energy. If I have a container, I shout onto it, ah, close it, I can't store sound energy inside because it doesn't occupy space. If I shine light on it through a flashlight and then close it, it's not like I can keep the light, because light it's not storable because it doesn't occupy space. So again, you have only 2 things in the universe: matter and energy. And the quarks and the leptons are the matter particles, and the gauge bosons and the scalar bosons are the interactions or force carriers that give rise to energy. For example, the gluon is the carrier for the strong nuclear force. The Z and W are for the weak nuclear force. The photon is for the electromagnetic force, and that's why we believe there is graviton here for the force of gravity, but we have not discovered that yet. And then Higgs is for this distinction between why some things have matter, some things have mass, and some things do not have mass. So for example, the electron is a matter particle. The photon is a particle. The electron is a particle, but the photon or light, the basic constituent of light, does not have mass, but electron have mass. So why would this have mass and that not have mass? That's because of the Higgs. The Higgs interacts with the photon, but does not. Sorry, the Higgs interact with the matter particles, but do not interact with the photon. That's why the photon does not have mass. So that's it. Again, I don't want to. Again, I sound like I'm bombarding you with all of this stuff, but again, the goal. I do not have this fantasy that you will understand what I'm saying. I do not have. I do not believe that you can understand all of what I'm saying. But I believe that you will be interested in it. That's the goal. I hope that because of this discussion, you will start to understand why physics is everything. Physics is the only science for some physicists, because if you really think about it, chemistry is simply just the physics of electrons and protons. Biology is just the physics of how biochemical signals, biochemicals in your body interact with neurotransmitters. So it's just really physics if you think about it. So that's why physics is the only science. It's the one that encompasses the very, very, very small, like elementary particles, to the very, very large, like the universe. So that's why go into physics, get a physics degree. Obviously, uh, I want you to do that, but at the end of the day, it's your choice. I'm just giving you a window of how interesting your life would be if you go into physics. But again, why did we get here? We are trying to explain where all of that starting hydrogen comes from. It's from here. And again, uh, we call this elementary particles, but some scientists believe that the most fundamental of it are actually the strings. So the strings actually vibrate to create these things, then build up the structure. But again, we have to understand this if we are going to try to understand the universe, because after all, this is what the universe is made up. It's made up of matter and energy. The force interaction carrier, the interaction of carriers, force carriers are what makes energy and energy possible, and these are what makes up the matter. Okay, so that's the idea there. In the next video, we are going to tie this up and try to explain what do we think of these particles and how do they come about.